Hey everyone, welcome to your own personal deep dive
Yeah, that's right.
into some really fascinating stuff.
Yeah.
Today we're going to be tackling the work of Bernhard Riemann.
Oh, yeah.
This guy was a mathematician, and not only did he revolutionize a bunch of fields, but he also shaped how we think about the universe.
Yeah, I mean, Riemann's work is really fascinating because it bridges this gap between abstract math and, the physical world.
Yeah.
He found these connections between, curves and surfaces and the fabric of space-time itself.
Yeah, it's kind of like he discovered the secret code that links the language of math to the actual reality we live in.
Right.
So the source material we're working with is a chapter from a book about Riemann,
Okay.
and it gets into the nitty-gritty of his ideas.
Yeah.
We're talking in topology, complex numbers, even the mysteries of prime numbers.
Yeah, our goal today is to give you a clear understanding of these concepts and why they still matter so much.
Yeah.
Even if you're not like a math whiz,
You're right. We're not going to overload you with equations.
No.
We're going for those aha moments.
Exactly.
So get ready to really stretch your brain.
Yeah.
Because we're tackling some seriously big questions can math actually help us understand the shape of the universe?
Right.
And what on earth do prime numbers have to do with any of this?
Yeah. Riemann's big breakthrough was seeing mathematical functions as deformations.
Okay.
He imagined them as ways to twist and stretch and reshape surfaces and curves.
So instead of just equations on a page, he was thinking about how those equations could actually change things visually.
Exactly.
Morphing a sphere into a cube.
Precisely. Or imagine a donut shape,
Okay.
like a torus being stretched and pulled into an ellipse.
Uh-huh.
Riemann saw functions as the tools to make those changes happen.
Okay, I'm starting to see it, but why is that such a big deal?
Well, because this idea, which seems pretty simple,
Yeah.
actually had huge implications for tons of areas of math.
Okay.
It opened up whole new ways of thinking about geometry and analysis.
Okay, so this is where we start diving into the deep end, right?
Yeah.
Let's talk about complex numbers.
Okay.
So our source material explains that they have two parts, a real part and an imaginary part.
Right.
It's they're points on a plane, not just a number line.
Exactly. And the problem is visualizing complex functions when they're applied to this entire infinite plane.
Right.
It gets unbelievably difficult.
Yeah.
It's like trying to draw a map of forever.
Yeah, my brain is already doing backflips.
I know.
Just thinking about that. So how did Riemann tackle this?
Well, he came up with his genius solution, Riemann surfaces.
Okay.
These are special surfaces where each point represents a single output from a complex function.
Okay, slow down for a sec.
Sure.
Could you walk us through an example
Yeah.
to make that a little clearer?
Of course, think of the cube root function.
Okay.
With normal numbers, it's straightforward.
Yeah.
But complex numbers have 3 cube roots for every input. Imagine trying to plot that on a flat plane.
Yeah.
Just be this jumbled mess.
Total pain.
Exactly like trying to untangle this giant ball of yarn.
Yeah.
So Riemann's surface for the cube root function is like taking 3 sheets of that complex plane
Okay.
and stitching them together in a very specific way.
Okay.
This creates a surface where each point has only one cube root,
Okay.
and it just clears up all the confusion.
So instead of being stuck on that flat plane with outputs overlapping,
Right.
we've moved to this 3D surface where everything has its own distinct spot.
Exactly.
That's pretty clever.
Yeah, and these Riemann surfaces weren't just a way to tidy things up.
Okay.
They revealed these hidden features. Points where the functions behaved in these unexpected ways.
Okay.
Mathematicians call these anomalies.
Anomalies, those sound like trouble.
Yeah.
Or maybe clues to something deeper.
Right.
What did Riemann make of these strange points?
Well, he saw them as key insights into the nature of the functions themselves.
Oh.
They pointed to these deeper mathematical truths that were hidden in plain sight.
So it's those anomalies were these signposts?
Yeah.
Pointing towards even more mind-blowing discoveries.
Exactly. And that leads us to another major area that Riemann influenced,
Okay.
topology.
Okay.
This is the study of properties that don't change even when you deform shapes, as if they were made of rubber.
Oh.
Imagine stretching and twisting a rubber sheet.
Okay.
Some things, like the number of holes, stay the same no matter how much you distort it.
Okay. That's topology in a nutshell. And I bet you have a classic example up your sleeve.
Of course. The 7 bridges of Königsberg problem.
Ooh, I've heard about this.
Yeah.
It's that puzzle about walking across bridges.
Precisely in the 18th century, the city of Königsberg had these 7 bridges
Okay.
connecting different parts of land.
Uh-huh.
And the question was, could you walk a path crossing each bridge exactly once?
Okay.
And so this mathematician, Leonhard Euler, crack this puzzle.
Okay.
And he showed that whether such a walk was possible depended only on the arrangement of the bridges and the land masses,
Okay.
not their actual shapes.
So whether the bridges are straight or curved doesn't matter. It's just how they're connected.
Exactly.
That's pretty cool.
Yeah. And Riemann took this concept to a whole new level,
Okay.
applying it to surfaces.
Okay.
Think of a donut or a torus, as mathematicians call it.
Okay.
You can cover it with these deformed circles,
Okay.
each carrying its own coordinates,
Okay.
like pieces of a map.
Uh,
These are called charts in mathematical terms.
Instead of street names and grids,
Right.
we're talking about mathematical coordinates wrapped around a donut.
Exactly.
I like that. That's a delicious image.
And Riemann used this idea of charts to define dimension in a very elegant way.
Okay.
If you can cover a space completely with these deformed circles, it's two-dimensional, regardless of how weird the shape might seem.
Wow. So we've gone from deforming shapes to understanding dimensions.
Yeah.
And all of this ties back to those complex functions and Riemann surfaces.
It does.
Like this giant interconnected web of mathematical ideas.
It is, and Riemann was just getting started. I mean, he was about to make an even bigger leap, applying these ideas to something truly mind-boggling.
Okay, I'm officially on the edge of my seat. I feel like I'm falling down this rabbit hole of higher math, but like in a good way.
Yeah.
Lead on.
All right. So Riemann took this idea of curved surfaces
Yeah.
and applied it to the biggest thing imaginable, the universe itself.
Whoa.
He proposed that our universe could be a three-dimensional variety,
Okay.
a space that might be curved in ways we can't easily perceive.
Whoa, that's a massive jump.
It is.
I mean, I can kind of picture a curved surface,
Yeah.
but a curved three-dimensional universe.
Right.
That's like next-level abstract thinking.
It is. To grasp this, let's try an analogy.
Okay.
Imagine beings living in a two-dimensional world, like characters in the book Flatland.
Okay.
They can only move forward, backward, left, and right.
Okay.
No up or down for them.
Okay, I'm picturing like little flat shapes.
Right.
Scooting around on a piece of paper.
Now imagine they live on a sphere,
Right.
but they're completely unaware of it. They lack the dimension of height, so they can't see that their world is curved.
It's like ants crawling on a basketball.
Exactly.
Totally oblivious to the fact that it's round.
Exactly. How could those Flatlanders ever know their world is curved if they can't step outside of it?
That's a mind-blowing thought.
Yeah.
And I guess it makes you wonder, are we like those Flatlanders,
Right.
stuck in our three dimensions, potentially missing the bigger picture of the universe's true shape?
That's the question Riemann was grappling with.
Yeah.
Our source material points out that those 2D beings could detect the curvature of their world by noticing deviations from the Pythagorean theorem.
Okay.
You know, a squared plus b squared equals c squared.
Ah, good old Pythagoras. I remember that one from geometry class.
Well, the Pythagorean theorem only works perfectly on flat surfaces.
Right.
If those Flatlanders tried to apply it to a really big triangle on their sphere, the math wouldn't quite add up.
Okay.
That discrepancy would be their clue.
So are scientists today trying to do the same thing with our universe? Like measuring triangles in space to see if they follow the Pythagorean theorem?
In a way, yes. They're looking for similar deviations by studying light from distant objects.
Okay.
If the universe is curved, the path of that light would be slightly bent.
Okay.
And that's what they're trying to detect.
So is the jury still out?
It is.
Do we live in a giant cosmic basketball?
Right.
Or is space flat?
The evidence is inconclusive. It's incredibly hard to make measurements on a cosmic scale with enough precision to tell if those tiny deviations are real or just measurement errors.
Okay, so the shape of the universe is still a mystery.
It is.
But what was Riemann's takeaway from all this? What was he trying to tell us about physics?
Riemann believed that the laws of physics should be expressed in terms of the geometry of space itself, not just forces acting at a distance, which was Newton's view.
So he was saying that gravity, for example, isn't just some mysterious force pulling objects together,
Right.
but rather a consequence of how space-time is shaped.
Yeah.
That's a pretty revolutionary concept.
It is. And his work laid the groundwork for Einstein's theory of general relativity,
Oh, wow.
which describes gravity precisely as the curvature of space-time caused by mass and energy.
Mind officially blown.
Yeah.
But now we need to shift gears to a topic that seems totally unrelated, prime numbers.
Okay.
I know they're important in math,
Yes.
but what on earth do they have to do with the shape of the universe?
That's the beauty of Riemann's work. He was able to see connections where others didn't.
Yeah.
Remember those anomalies we talked about on Riemann surfaces?
Yes.
Well, he found a surprising link between them and the distribution of prime numbers.
Okay, before we go any further, let's do a quick refresher for our listeners.
Okay.
Prime numbers are whole numbers greater than 1
Right.
that are only divisible by 1 in themselves.
Right.
2, 3, 5, 7, 11, and so on.
Yeah, they're like the atoms of the number world.
Exactly. Their definition is simple.
Yeah.
But how they're sprinkled throughout all numbers is incredibly complex and seemingly random.
Yeah.
There are hints of patterns, but they're incredibly subtle and difficult to pin down.
Exactly.
So where do Riemann surfaces fit into this numerical puzzle?
Well, Riemann developed a special function called the Riemann zeta function.
Okay.
Believe it or not, this function has deep connections to the distribution of prime numbers.
Okay.
It's a complex function, meaning it takes in and spits out complex numbers.
Right.
And when you visualize this function on a Riemann surface, guess what?
What?
Those anomalies, those special points we talked about earlier, they pop up.
Okay. I'm trying to follow along here.
Yeah.
So a complex function visualized on a Riemann surface
Yes.
reveals something about prime number.
Yes. It's like those anomalies hold clues to the secrets of these fundamental building blocks of numbers.
Okay.
Precisely. And it gets even wilder.
Okay.
Riemann formulated a hypothesis about the location of all the non-trivial zeros of this zeta function.
Okay.
In essence, he proposed that all those special points, those anomalies, lie on a specific vertical line on the complex plane.
Wait a minute. So we've got prime numbers, a complex function, a Riemann surface, and the location of points on a plane.
Yeah?
And this is all connected.
It's like a giant interconnected puzzle.
Wow.
And while Riemann's hypothesis is still unproven, mathematicians believe that if it's true, it would unlock incredible insights into how prime numbers are distributed. It would be a major breakthrough in number theory.
This is incredible. It's like Riemann was a mathematical detective piecing together clues from different areas of math to uncover these hidden patterns and connections.
And the stakes are high. Proving Riemann's hypothesis is one of the Millennium Prize problems,
Okay.
with a $1 million reward for whoever cracks it.
So solving this mathematical mystery could make you a millionaire.
That's right.
Now that's a math problem I can get behind.
Right.
But let's not get ahead of ourselves.
Okay.
We've covered a lot of ground today, and I think it's time to take a step back and recap what we've learned on this whirlwind tour through Riemann's mathematical universe. Okay, so let's take a breather and recap what we've learned about Riemann.
Yeah.
His idea of functions as deformations, these tools that can twist and mold shapes,
Right.
those revolutionized fields like complex analysis and topology.
He gave us these intricate Riemann surfaces, you know, a way to visualize complex functions that would otherwise be impossible to grasp.
Right.
And he helped us understand the concept of dimension in a whole new way.
And then he just blew everyone's mind by saying that the universe itself could be a curved three-dimensional variety.
Yeah.
Like a space that might warp and bend in ways we can't even perceive.
While we still haven't definitively determined the shape of our universe,
Right.
Riemann's work laid the foundation for Einstein's theory of general relativity,
Yeah.
which completely changed how we think about gravity.
And then just when we thought things couldn't get any more mind-blowing, we dove into the mystery of prime numbers
Right.
and Riemann's famous hypothesis.
Who would have guessed that these seemingly random numbers could be linked to complex functions and those crazy Riemann surfaces?
It's what?
Yeah. It highlights a key takeaway from all of this. Seemingly unrelated areas of math can be profoundly interconnected,
Yeah.
and those connections often lead to these unexpected breakthroughs.
I think that's what's so amazing about Riemann's work. You know, he was able to see these hidden connections, like these bridges between different mathematical worlds, and use them to push the boundaries of human knowledge.
And his legacy extends far beyond just abstract theorems and
Oh,
equations.
yeah, for sure.
His work has practical applications in fields like physics, engineering,
Yeah.
and even computer science.
Exactly like cryptography,
Right.
which relies heavily on prime numbers to secure our online communications and transactions.
Exactly.
So if Riemann's hypothesis is proven, it could have a huge impact on cybersecurity.
Yeah, making our digital world even safer.
So if you're listening to this and you're thinking, why should I care about all this?
Yeah.
Here's why Riemann's work shows us that even the most abstract ideas can have real-world implications, and that the pursuit of knowledge, even in the realm of pure mathematics, can lead to incredible discoveries that shape our understanding of the universe and our place in it.
It's a reminder that there's always more to learn, more connections to uncover, more mysteries to solve.
Exactly. Now here's a final thought to leave you with. if the shape of the universe is indeed linked to the laws of physics, as Riemann believed? Could there be other mathematical structures out there just waiting to be discovered that hold the key to unlocking even deeper mysteries? Something to ponder as you continue your own exploration of the vast universe of knowledge. This has been your personal deep dive into the fascinating world of Bernhard Riemann. Until next time, keep exploring of your floor.